Okay, so we will now start our lesson on inverses. So we will, I'll first do inverses in two parts. So this part will be on defining inverses and basically doing the 2 by 2 case. And then the second part will involve finding inverses for larger matrices. All right, so let's start with the introduction on inverses. So first of all, let I of n be equal to the identity matrix. So this is the matrix with ones down the diagonal and zeros everywhere else. So this is an n by n matrix. Okay. So first of all, we let A be a square matrix. And so we say a matrix is invertible if there's a C such that A times C is the identity and C times A is the identity. So actually, let's suppose there exists a C, which is an n by n matrix, such that we have A times C being the identity and C times A to be the identity. Okay, so this doesn't always happen, but let's just assume that it does just for now. All right, so let's say there's another matrix which actually does the same job. So suppose there exists another square matrix such that the same relations hold. So A times C prime is the identity and C prime times A is also the identity too. All right. Now, my claim is that C and C prime have to be the same. All right. So how can we show that? Well, the first thing we could do is we could take this equation and this equation, and we can actually combine them. So we have that AC is equal to A times C prime, right? And now what we can do is we can hit by C on both sides. So this implies that C times AC is equal to C times AC prime. And then what we can do is we can just combine these. So that means that CAC is going to be equal to CAC prime. Now we know C times A is the identity, right? So identity n times C is equal to identity n times C prime. So C is equal to C prime. All right, so if you have another matrix which satisfies the same properties as C, then the matrix had to be C itself, right? So what we're going to do then is we're going to call such a matrix A inverse. So without ambiguity, we can write A minus 1. And so if these conditions hold, then we say a matrix is invertible. So if star holds, then we say A is invertible. Okay. And let me just kind of summarize this. So if A has an inverse, namely it's invertible, then A inverse times A has to be the identity, and that has to be equal to A times A inverse. Okay, so So sometimes in the literature, they use the word singular and non-singular. So non-singular is the same thing as invertibility. So we say that A is non-singular if and only if A is invertible, okay? And if A is singular, which is not non-singular, then A does not have an inverse. All right, so let's go through some cases, the 1-by-1 case and the 2-by-2 case, and analyze that thoroughly. Okay. So let's start with the 1-by-1 case. So this is the case that you have actually seen before, probably in elementary school. So here A is a 1-by-1 matrix, which is just a single number A. Okay. So the question is, when is A invertible? Well, I think you guys all know the answer to that. It's namely when A is not 0. So here, A inverse is just 1 over A. Right? So the inverse exists infinitely if A is not equal to 0 in that case. Okay, so here A cannot be 0. Okay, and if A is equal to 0, then it's singular. All right, so let's do the 2-by-2 case. All right, so in that case, the A is a 2-by-2 matrix. That's A, B, C, and D. And we have something which we'll later call the determinant, but for now, which is just some number. And that number is the following. So if AD minus BC is not 0, then what I can do is I could define A inverse. And so I claim that the formula for A inverse is 1 over AD minus BC. And what you do is you interchange the A and the D. So that's D times A, and you negate the B and the C. Okay? So I claim that this is actually the inverse. Well, how do we show it's the inverse? Well, just multiply times A and make sure you get the identity back. So let's do that. Okay, so we do it one way and we do it the other, and it's similar. So I'll just do one side first. So A times A inverse, what's that? So that's going to be, I can multiply the scalar out. AD minus BC. A is A, B, C, and D. And then times this other stuff. So D minus B minus C and A. Okay? And then you have 1 over AD minus BC. And now we matrix multiply. Okay, so the first row, AB dot D minus C, that's AD minus BC. Okay, that looks pretty good. Then I take AB, dot it with minus A, minus BA. Well, that's going to be 0. And then CD dot B minus C, that's going to be 0. And then finally, you get the last one being AD minus BC. So lo and behold, you get the 2-by-2 identity matrix. Okay. And then the other computation is similar. Okay, so you can actually do that yourself. All right, so this is the formula for the inverse. All right, so for 2 by 2, we have this nice nifty little formula. And now what we can do is we can apply it to an example. Okay, so the example is the following. So find the inverse of the matrix A, which is 3 minus 7 and minus 6, 13. Okay, so to find A inverse, what do? I take 1 over AD, 3 times 13, minus 7 times minus 6. Okay, then what do? I reverse A and D, and then I negate the BC entry. So that's 7, 6. Okay, and then what do you get? So you get 1 over 39 plus, actually minus 42. Okay, so that's minus 3. So that's minus the third times this. Okay. So it's not too hard. So why are inverses important? Well, I kind of indicated this in the last session. Namely, what you can do is you can solve systems of equations. So let me put why are inverses important? Okay, so let's say I take a system of equations. So AX equals B. And here I'm going to assume that A is an m by n matrix. So this is an m by n system. Okay, so this doesn't hold for arbitrary systems where m and n aren't the same. All right, so suppose we have an inverse. Okay, so just like the problem at the end of last time, I can hit on both sides with the inverse. So I take A inverse AX, A inverse times B. Okay, and then you can associate this side, and this is going to be A inverse times A times X, and that's the identity. So that means that identity times X. And then, well, you have the solution now. So X, the vector X is going to be equal to A inverse times B. And this is the solution. So whenever you have, ooh, that doesn't look so good. Let me fix that a little bit. Apologies. It looks a little better. I'm not in pandemic mode, so I don't draw as straight as I did during the pandemic. Okay, so so here's the solution. So whenever A is invertible, then you have a unique solution, namely A inverse times B. Okay, so let me just summarize. So this is the conclusion. So if A here is non-singular, namely invertible, okay, then AX equals B has a unique solution. comma, namely, x equals A inverse times B. Okay, so what I'm going to do is we'll actually apply this principle to a system of equations. So here's an example. Okay, so solve the system of equations. And I'll give you the system right now. So 3x minus 7y is equal to 10. And minus 6x plus 13y is equal to 2. All right, so first of all, let's put it in the more compact form. So the more compact form is 3 minus 7 minus 6, 13, and x and y, and that's equal to 10, 10, 2. Okay, so this is ax equals b. Now, question, is A invertible? Well, if you look back up here, this A up here is the same as the A down here. And we actually computed the inverse already. Okay, so this is going to be A. It's easier when I have a chalkboard. I can actually, you can like see things better that way. And so we know that xy is going to be equal to A inverse times 10, 2. Okay. Now, we did compute A inverse, and that was 1 over 3. And then we have 13, 7, 6, and 3. And this is 10 and a 2. And when you compute this all out, what do we get as a vector here? Well, you could take the dot product, 130 plus 14, that's 144. And then the dot product is 6, 3 with 10, 2, that's 60 plus. Is that right? 60 plus 6. Ooh, is that right? Sorry, I'm just looking at my notes here. So 6 times 10 plus 3 times 6, that looks like it's 66. Let me just make sure. 10 to, yeah, looks right. Okay, so that's the answer. This is not correct. Correct me later on this. Right. So the last thing I want to do is I want to just state some properties for you. And then we'll be finished with this session. Okay, so property number 1. So if I take A inverse and if I invert it again, then I skip back to where I started from. 2, if I take AB inverse, so this is like the transpose property. You just have to put the inverses in the opposite order. And then 3, if you take A transpose inverse, this is the same as interchanging A inverse in the transpose. All right, so all of these are proved the same way. What you do is you actually show that one side is the inverse of the other. Okay, so let's do justification of, let's just pick one. Let's pick number 3, for example. All right. So if I take A transpose, and if I look at A inverse transpose, okay, so remember, A transpose inverse is the inverse of A transpose. So if I show this one actually equals identity, then by uniqueness, we're done. Okay, so let's do that. So the first thing is, what do we know about the transposes? Well, if I take B transpose, A transpose, that's A times B transpose, right? So that's going to be A inverse A transpose. Okay, so this is by the property that we did in the last class. And of course, A inverse A is identity times transpose to the transpose, and that's just the identity matrix itself. Because the identity matrix is a diagonal matrix, so its transpose is itself. Okay, and then similarly, you'll get A inverse transpose A transpose. That's going to be identity too. So hence, by the uniqueness that we proved at the beginning, we have to have that A transpose, the inverse of A transpose, has to be equal to A inverse transpose. Okay. All right. So that concludes the introduction for inverses and the analysis for the 2x2 case. So I will make another video which actually shows how to compute inverses for the arbitrary n by n situation, and that'll use Gaussian elimination.